It's recorded. So the speaker is Laszlo Feher from Ötvös University, Budapest. Go ahead.
Thank you for the invitation. And sorry, I thought that I still have almost an hour. I messed up the time, but luckily you were looking for me. So Plücker formulas or Plücker numbers are very classical stuff. Almost 200 years ago, this story started, and it, like the two most basic question is, if you have a degree plane curve, projective plane curve, what is the number of bitangents and what is the number of flexes? So I can show you a nice picture of the bitangents for d equal to 4. So notice that for d equal to 3 it doesn't make sense. Cubic curves doesn't have bitangents. So the idea is that I start with this degree 4 curve, but this is not smooth. I will be interested in generic curves. So I perturb it a little bit. So I get this picture, the red one. This is called the Hilbert quartic. And it's not very difficult to show that it has 28 bitangents. Here is a little doodling why this is. So if you pick two components, then you get 4 bitangents. So that's 4 by 4. That's okay. So I think that's not enough. Okay. So you can pick two components in 6 different ways. So it's 6 times 4, it's 24, and there are 4 bitangents like this one, where you use only one component. So you can ask me to show the flexes. Unfortunately, there is no picture for the 9 flexes of a degree 3 curve, of a cubic curve, because Felix Klein proved it that only 1/3 of the flexes can be real. But later I will try another roundabout way to explain you these 9 flexes. So the first thing, when we want to kind of have more interesting problems, to increase the dimension. So instead of curves, I'm looking for hypersurfaces in the projectivization of Cn. And then I will have tangent lines with more interesting multiplicities. There is a little picture here. So if the dimension is high enough, then you can get all kind of multiplicities. So to somehow formalize the situation, let V be a plane, a two-plane. So it corresponds to a line, a projective line in the projective space. And we say that this is a lambda line for the hypersurface ZD. So ZD is just the generic degree D hypersurface. If the restriction of the defining function f, which is necessarily the product of linear terms, have these multiplicities. Okay, so we can expect finitely many lambda lines if the codimension is equal to the dimension of the space of lines. So the space of lines is a Grassmannian, which has dimension 2 times n minus 2. It's a 2 Grassmannian. And the codimension of the variety of lambda lines is the sum of lambda I minus 1. You can think of it as when you increase the multiplicity from 1 to higher, then every time you add an extra condition. So the number of lambda lines is denoted by this PL Plücker lambda D, because I will be mostly interested in the dependence on D of these formulas. So notice that here, oops, sorry. Here I take a partition which doesn't contain 1. Okay, I use the exponential notation. So I count in the partition, I count the 2's. There are E2 of 2's and so on. But there is no 1 because I want to stabilize the whole situation. So I can add as many 1's as I want. Then I have to increase the dimension of the hypersurface, but I don't change the lambda. So this is how we obtain the original Plücker formulas, then take the shape of these two. Okay, so this is the bitangents belong to the lambda equal to 2, 2, and the flexes belong to 3. Okay, and the main result I would like to talk about in the first half hour. Okay, so maybe I will ask Richard to tell me when half an hour is over. Can I ask
Okay,
you that? Thank you.
sure.
So this result I would like to talk about is that this is not an accident. These Plücker numbers always depend polynomially on D. In fact, we can calculate the order of this polynomial, which is always at most the size of the partition, but sometimes smaller. I will don't give you the exact result, just an example. And we can also calculate the leading terms. So in some sense, we understand the asymptotics of these formulas. So the extreme case is when the partition has a single part, which is I call them, and I think it's other people use it as well, the M flexes. So, so an M flex is a line which has a single point where the multiplicity is higher. And in this case, this multiplicity is M. So in this special case, we have a closed formula. Now, this formula looks nice, just I think I have to explain what this thing is here. Okay, so this is a Stirling number. Yeah, I will talk about Stirling numbers in a moment. So in general, there are no closed formulas for these polynomials, and I don't expect that somebody else will find them. These are complicated, and I think I will kind of explain you why these formulas has to be complicated. Okay, so what is the method? The classical method to work with these Plücker formulas is to define a variety of tangent lines. So I take basically all, I take all the lambda lines of a given hypersurface. So this is a subset of the space of lines, which is a 2 Grassmannian. Yeah? And we calculate a cohomology class, or for people who prefer the algebraic geometric notation, the Chow class of this variety. And if it's finitely many points, this variety of tangent lines, then the Plucker number is given by this integral. Okay, so how can you calculate this guy? You need to find a resolution of this variety, even if it's not zero-dimensional. So the first modern approach to this problem was in this paper of ours with Richard Rimani and András Németi, but independently two other methods were established by Balázs Kőműves and Maxim Kazarian. So the idea is that somehow we work universally. So we look at all the polynomials, the homogeneous polynomials on C2 of degree D. So this is the notation. And we look at the so-called coincident root strata. So we look at these polynomials with the given multiplicities. So again, let me remind you that all homogeneous polynomials in two variables split into linear terms. So that's why this is not very strange to have this specific shape. Okay, so if I have a GL2 invariance of variety of my vector, of my representation, so GL2 acts on everything here by reparameterization of the variables. So if in this situation, then we can assign an equivariant cohomology class to this variety, which is a polynomial in the variables C1 and C2. Okay, and the key property of this polynomial is that the cohomology class of the variety of tangent lines can be obtained by substituting into this polynomial the Chern classes of the tautological bundle. Okay, so this is the tautological bundle. And this is a very classical idea that if I have a hypersurface, then the defining polynomial will define a section. Maybe I should write this here. So ZF, I have the ZF. F defines a section of all the S2, this bundle over the Grassmannian. Okay, and the Y lambda locus of this section is exactly the tangential variety. And if someone doesn't know what equivalent cohomology is, well, I just defined it. So if you believe me that there is such a polynomial, then this property uniquely defines the polynomial. Okay, so in some sense, our job is to give some nice formulas for these cohomology classes. So in this classical paper written almost 20 years ago, what we did was we used a projectivized version. So we gave a resolution of the projectivization of Y lambda by collecting the multiplicities and taking this product of projective spaces. So this is very elegant. And also, if we have this resolution, then we can calculate the push forward by using the Etiapod integral theorem. So it's very simple, but the answer is very complicated. So unfortunately, these integral formulas have two problems. One is that there are too many fixed points, and every fixed point generates an extra term in a sum. And the other is that these terms are rational functions. And even for the computer, it's difficult to add rational functions. So even though in this paper with Richard and András, we managed to prove what we wanted about relations in certain quotient spaces, but for proving polynomiality, it's just too complicated. So we needed another method. And the new method was finding another resolution. In fact, it's not exactly a resolution, it's a branched covering. So it's EM to 1. So remember that these are the multiplicities. EM is the number of points with the highest multiplicity M. Okay, so don't get yourself get scared of this resolution. What is or branch covering? It's essentially just multiplication by a linear, the mth power of a linear factor. So this d prime here is d minus m. So I take a polynomial which has degree d prime, and I multiply it by the mth power of a linear term. And this way I get a polynomial of degree d. So if you want to do everything carefully and equivariantly, then you have to use this bundle here, which is the quotient bundle over the base P1. So it's still a very, very simple bundle, but you need this twist to get this branched covering. So as soon as you establish that this is indeed a branched covering, which is very simple, and you calculate the push forward, then you obtain the following theorem. Okay, so this is just a careful way of writing down how to push forward. So what is happening here, this is an inductive formula. So you have this lambda prime, which is obtained from lambda by removing the largest multiplicity, the point which has the largest multiplicity. So we assume that we already know the cohomology class of this guy. And this formula tells us how to calculate out of this the cohomology class of y lambda. Okay, and it's fairly simple. You make some funny substitution into this formula, which is described in the first line. And then you multiply it with something which looks like an Euler class. So it's a product. This is this product here. And then you take the divided difference operation. And then you divide by 1 over EM. This is because it's not a resolution, but a branched covering. So the thing is that if lambda is small, you can even calculate this by hand. Just one by one, you add these higher multiplicity points, and very quickly you get the formula you are interested in. And the computer is very fast with this, so you can very quickly calculate even more than you want. Now, maybe this is a point where I can talk about how we ended up with this theorem. Actually, what we first wanted to do is we wanted to study the CSM classes of these coincident root strata to calculate something that instead of calculating the number of lambda lines, we wanted to calculate the Euler characteristic of the variety of tangent lines. And after many failed attempts, it turned out that this is the right approach to use this branched covering here. And only after we figured this out, we realized that, wait a minute, even these Plucker numbers are not known to be polynomials, so we went backwards. In fact, this is a kind of main theme of this story, because you will see that we had to move backwards even one more step, even to one problem which I was completely sure that it turned out that it's not. Okay, so this is how we got to this resolution. And when we studied these numbers, we found something which should be extremely classical, but we didn't find any sign of this theorem. That there are two very classical enumerative problems. What, Richie, how much time I have?
Another 8 minutes before the break.
Okay, excellent. So I can study the number of lines on a generic hypersurface with these given constraints. Or I can study these hyperflexes, which on hyperflex I mean that these are lines with maximal multiplicity, so it means lines which intersect our hypersurface only in a single point. So it will have multiplicity, well, there are some typos, multiplicity D. Okay, so the famous example is that a cubic curve has 9 flexes and the cubic surface has D times 9 lines on it. So there is some funny thing, I never thought about it, that there are famous models of cubic surfaces on which you can see these 27 lines. They can be real, but the flexes cannot be real. So I'm still not sure why this is. But I want to emphasize that this theorem in this form is almost trivial. So if you understand a little bit about how to calculate these cohomology classes, it just shows itself immediately. Okay, so maybe I mention some other enumerative problems. So the idea is that you can somehow create a more complicated branched covering by applying this construction to every fiber of this vector bundle, the tautological bundle. So basically, in the previous formula, in the previous diagram here, you replace C2 by the tautological line bundle. This will have the effect that the base will change from the projective line to a partial flag manifold. And using this construction, you can calculate more complicated numbers like, sorry, it should be pencil. So if you have a pencil of degree D curves, then if you look at the bitangent lines, but you are only interested in the points where the bitangent lines are tangent to your hypersurface, then you get a curve. And the dimension, the degree of this curve is given by this degree 3 polynomial. And turns out that uh, our approach is in some sense more flexible than the original approach, which is extremely similar to this one, but much more difficult to introduce, especially because this bundle doesn't show up. Sorry. This bundle here doesn't show up explicitly in the classical approach. Instead, what shows up is the bundles of principal parts. And I still don't know if what is on this diagram is a bundle of principal parts or not. The Chern classes are the same. Okay, so this was my plan for the first half an hour.
Excellent, excellent. So let's have a 5-minute break. Is that the usual length, Anders? No? And then we resume then.
Yes, that is very good. Hopefully that's compatible with another cup of tea.
Yes, I definitely need it. So I'm coming back in 5 minutes.